Thanks, everyone. Also, thanks so much to the organizers for inviting me to give this talk. I'm very excited that I came here. I didn't know any of the people at this conference before this, and now I've met so many of you. That's great. And I also got to see dingoes, and they left mud on my pants. So that was also very nice. So today I'm going to talk to you about some work that I've been doing both as a postdoc and during my graduate studies, studying the Mira distance ladder and using HST and James Webb Space Telescope for that. So this is work I've done in collaboration with Wenlong Yuan, which some of you might know, Adam Rees, Massimo Marengo, Patricia Whitelock, who couldn't be here, I guess, and many others. And so this image in the background is actually not from HST or JWST, and it's actually not a galaxy that I studied. It's a small Magellanic Cloud, but you will find out later why I think it's so important, and also it's just pretty. So since at this conference, most of you know more about AGV stars than me, I figured I could skip that section of the talk and focus more on distances. So I know everybody knows what distances are, but maybe you don't think about how useful they can be. But most of our measurements are relative. Like we get apparent magnitudes, we get angular sizes, but when we have a distance, we can take that and convert it into actual physical quantities like physical sizes or luminosities. So knowing the distance helps us break degeneracies between what we're observing. So this here is actually from a British show called Father Ted, which I haven't seen. I don't know how I found out about this, but Father Ted is explaining to a clueless guy that the kangaroos that he's holding, like the little figurines, are small, but the ones outside are large. And what this guy doesn't get is that the ones inside are nearby and the ones outside are far away. And that's why he can't tell just based off of the angular size of the kangaroos. So this is a problem we have in astronomy a lot, and thought it illustrated that very well. Okay, so a little bit of history. Maybe you do know that apparent magnitudes and angular sizes are not that useful, but distances have also been really fundamental in the development of cosmology as a whole, because it's helped us set the size and scale of the universe. So if we go back to the 1920s, there was the great debate where these two scientists, one of them who was the director of this, well, this was before the CfA, so the director of Harvard College Observatory, Harlow Shapley, believed that the Milky Way was the whole universe. And Herbert Curtis believed that these little things that they called spiral nebulae, which we now know are galaxies, were basically just like the Milky Way. So the Milky Way was only one of many in the universe. And Shapley is considered to have won this debate, but now we know that he's wrong, that the Milky Way isn't everything. And the way that this was decided is that a man named Edwin Hubble used Cepheids, an Andromeda galaxy, one of these spiral nebulae, to show that Andromeda was far farther away than they originally believed. And it was really far out of our galaxy. So the distance here literally changed what we thought about the size of the universe. So later, Hubble would go on to do other things with Cepheids, including making this very famous Hubble diagram. And basically what we have here is velocity, and actually it should be kilometers per second, but he didn't write that, I guess, against distance. And velocities, as many of you know, we can get from spectra. So that's generally considered the easier thing to do, but distances are tricky. And he used Cepheids here too to measure distances and velocities to a bunch of galaxies. And what he found is that the farther away they were, the faster they were moving away from us. So unless there's some grand conspiracy where every galaxy has been told to do this, what this actually means is that the space in between us and the other galaxies must be getting bigger. So in essence, he found that the universe is expanding. And this measurement's actually really bad. If you try to read it off the plot, the slope of this line is like 500 kilometers per second per megaparsec, which is many times larger than what we believe it is today. So he didn't do a very good measurement of this, but he did still find that the universe is expanding. Okay, so I talked about why we care. Now, how do we actually do this? So there's 4 basic ways that we know of to measure distances, and those are radar, which is where we have a known speed, so like light usually, and we measure the time it takes for it to get to something and come back. Parallax, which is where we have a known size, in this case, like the baseline that you're moving over some time, and you're measuring an angle, like the angle at which the object appears to move when you move through that baseline. And so that's just a geometric measure of distance. We have standard candles, which is where you have something of a known luminosity. And so then based off of how its apparent magnitude is, you know how far away it is. And then we have a standard ruler, which is where you have a known size, and then you measure its angular size, and now you know how far it is. So each of these methods is only appropriate in a certain range of distances. And radar, I think the record is the Earth to moon distance, which is like 385 kilometers or 385,000 kilometers. For parallaxes, you can make an argument that you can go farther, but in general, I would say about 5 kiloparsecs with Gaia. For standard candles, type 1a supernovae are probably the most reliable, out to about redshift of 2 when the universe was about 20% of the age it is now. And then for standard rulers, the biggest ones we have are baryon acoustic oscillations, basically leftover. It's the freezing of matter when it's separated from, decoupled from photons, and you can look at it in the density distribution of galaxies in the universe. And that's about 150 megaparsecs, and you can get out to, I guess, the surface of last scattering. So today I'll talk a little bit about these two because those are the ones relevant for Mira's, and I will briefly touch on why I don't think we can use parallaxes yet. So, okay, I would be remiss to have a talk about standard candles where I don't talk about Henrietta Leavitt. She was an early computer, that's what they called the women that were working at Harvard College Observatory, who is the person that discovered standard candles. She did this by studying the SMC, which I had in the background of my first slide. And she found that the variable stars in the SMC, a subset of them seemed to follow an interesting relation, where the longer their periods were, the brighter they were. And so since these stars were at basically the same distance, all being in the SMC, she was able to therefore conclude that this relation was intrinsic to the stars themselves. And so here what she actually used are provisional magnitudes, so we can't easily recreate this plot, but there are provisional magnitudes that are taken as the average of the max and min of the light curves of these stars against their log period shows a linear relationship. And this is the first PL diagram from her 1912 paper. I've also read that she's a wonderful lady. I don't know. Apparently she's a great person. I mean, she's dead, but yeah. So, so these Cepheids are what we call standard candles, which means that once we get their periods, which is generally distance invariant, because we're not looking at things at high redshift, we then know what their luminosity should be relative to other Cepheids. So we're essentially looking at the same candle farther and farther away, and based off of the comparison of its brightness, we can measure its distance. So Cepheids and other standard candles are like the heart of the local distance ladder. We call it the local distance ladder because we're measuring the expansion rate of the universe at the present day, and we're doing that directly. But there's another way to get a measurement of the Hubble constant, and that's through using a combination of studying the CMB, which is the leftover radiation from the Big Bang, and combining that with a cosmological model. So now our current best model is Lambda-CDM, which just means it includes dark energy and a cold dark matter. And cold dark matter is just not interacting with light, and it's moving much slower than the speed of light. So Lambda-CDM has been pretty good, and it's remained unchanged since the discovery of dark energy in the 90s, essentially. And when you take that and combine it with the CMB, you can sort of propagate forward to see what the Hubble constant would be today. And that's what we call an early universe measurement, but it's not exactly a direct measurement because it's model dependent. So what we're actually finding now, and what is called the Hubble tension, is that if you compare your early universe measurements with your late universe measurements, you find a discrepancy on the order of about 0.2 magnitudes, or 9%. And I don't expect you to read this whisker plot. This is just to show how many different ways people have tried, and it's not even a comprehensive list, to measure the Hubble constant. So because one is looking at essentially as far back as we can look, and the other is at the present day, cosmologists often call the Hubble constant an end-to-end test of the cosmological model. And you can see here, this is from a review that Adam wrote, that the early universe measurements and the late universe measurements, they should form this bridge if they agree with each other, but they don't instead. Okay, so now, one more thing I wanted to say is that the level to which they don't is actually about 5 sigma right now. And I want to quantify that a little bit by saying that we're comparing the Planck measurement, which is this red shaded thing here, the most precise early universe measurement, with this blue shaded region, which is given by the most precise late universe measurement, which is the Cepheid distance ladder from Rees et al. 2022. And so a lot of these other measurements on their own are not precise enough to give a significant result. So that's why we compared those two. But if you also look at the average measurement, you actually get something that's very, very significant. Okay, so this is the distance ladder that I described. It uses the Cepheid stars that Henrietta Leavitt first discovered, and it basically has 3 rungs. So as I mentioned, each way of measuring distance is only good out into a certain range. So at the shortest distances, you can use geometry, which gives you an absolute measurement, but it only works to nearby galaxies. In our case, geometry includes using masers in NGC 4258, which is at 7 megaparsecs or so. And then what you do is you use geometry to get distances to very nearby Cepheids in this case. And what I've done is using geometry to get distances to very nearby Miras. And then the next step is once you've calibrated the absolute luminosities of your Cepheids or Miras, you then observe these same stars in a type 1a supernova host galaxy. So type 1a supernovae are, well, you guys know what they are, but they are very famous standard candles that are pretty rare nearby us. So we have to use something relatively bright, like an AGB star or a yellow supergiant like a Cepheid, in order to actually measure the distance to a type 1a supernova, because there's none close enough that we could actually get a geometric distance to. And then from there, they are brighter than our primary distance indicators, our primary stellar distance indicators. So we can use them to directly measure the Hubble constant by looking at supernovae that are in what we call the Hubble flow. Like they're in galaxies that are far enough away that their recessional velocities are dominated by the expansion of the universe and not by peculiar local motions or interactions. Okay, so as I mentioned, the Miras that I'll be talking about today are relevant to these 2 rungs. Okay, so I don't have to spend long talking about this, but Miras are fundamentally pulsating TP-AGB stars. As we know, they're extended sources, so they have radius larger than 1 AU. This means that their parallaxes are smaller than their angular sizes, and they're also not very round looking. And we've seen lots of other pictures of this already. But this is partly why I think parallaxes are having some issues right now with these stars, but it's not the only reason. Sorry, this is, okay. So the 2 spectral subtypes of Miras, they don't follow the same period luminosity relation though. So here are the oxygen-rich ones that in black points and the carbon-rich ones in red. And you can see that The carbon-rich ones, especially at these shorter wavelengths like I, J, H, K, they have a lot more scatter. Now, this actually looks extra bad because all of these are single epoch measurements, but I just like this plot because you can really see how it looks across the wavelength spectrum. So it's important when we want to study the PL relation to separate these two types. And I've also included a light curve here so you can see what they look like in visual magnitudes. Okay, so these stars also have very long periods ranging from between 100 to 1,000 days or even longer. They have large amplitudes in the V band. Sometimes they can even get up to 10 magnitudes. And they follow very tight PL relations, meaning the scatter is like about 0.12 magnitudes in the infrared or near infrared. And as you can see from here, from this great review paper by Patricia Whitelock, Cepheids in the near infrared are about the same brightness as Mira's. So that means we can actually go to the same distance. And they're, of course, brighter than tip of the red giant branch stars. So up here, you can see a comparison between the Cepheid distance, the Cepheid PL relations, and the Mira PL relations here. You can sort of see that it's not linear at longer periods, probably due to hot bottom burning. And these are the carbon-rich Miras that don't really have a PL relation in, not a good PL relation in K-band. Okay, so if Cepheids are so great and they already have the most precise distance measurement, why do we even need to look at Miras? Well, and in my case, since we're trying to do cosmology, the bar for new physics is high. So at some level, even if you just keep making one measurement more and more precise, you want to have other independent measurements that can serve as a cross-check. So it's really useful to have all those other measurements that like sort of, oops. Okay, so it's very useful to have other measurements with different methods so that we're not subject to the same systematics. Secondly, Cepheids are young stars. They're yellow supergiants. So they're really only found in galaxies with recent star formation. And that means that usually the HST Cepheid sample is in spiral galaxies, for example, whereas AGB stars are more ubiquitous. So we can look in elliptical galaxies as well. And that increases our potential for increasing the number of local type 1a supernovae that are calibrated, because now we can calibrate ones in galaxies that Cepheids couldn't reach initially. And then Cepheids are also detected in the optical, where their light variations are larger. Those variations are much smaller in the near infrared. In fact, you pretty much can't find Cepheids as variables using only near infrared time series data. So with HST getting up there in age, it's going to be a very good alternative for the upcoming IR missions like Roman and for the current James Webb to use Miras because you don't need optical data. And then the other thing is that all other primary, and by that I mean like the second rung stellar distance indicators, the ones that can be directly measured with geometry, are fainter than Miras because these are generally TRGB, carbon-rich Miras. I know they're brighter in longer wavelengths, but at near-infrared wavelengths, R Lyrae, etc. So those all have an even smaller observable volume. And in the volume that we can look at with Cepheids already, type 1a supernovae are only occurring at about 1 a year. So that rate's even lower for these other distance indicators. So here's what the Mira distance ladder with HST actually looks like. We have two anchors, like two galaxies where we have geometric measurements that we use to calibrate the absolute magnitude of the PL relation. And that's NGC 4H58 and the LMC, where we use detached eclipsing binaries. And then two type 1a supernova calibrator galaxies, so galaxies that were host to recent type 1a supernova with good photometry. And that's NGC 1559 and M101. So I'm actually not going to talk about the LMC today, but we do use it in the distance ladder. But most of this work was done with ground-based data. Okay, so 4258 is best known as a mega-maser host galaxy. That's because it is the nearest mason galaxy that has a very precise distance, and that distance is 7.5 megaparsecs. It's precise to 1.5%, which is pretty amazing. And because of that, we went and looked at Miras in this galaxy using WFC3 IR observations in HST H and J band. And we had observations that spanned about a year. And we also took some archival observations of from ACES that were optical, that were taken about 10 years earlier. And we had one more F-160 image from a mosaic that was taken in 2009. So basically cobbled together all the data that we could. And the result is that we were able to find stars that were clearly varying in magnitude, as you can see here. And this is the light curve of one example star. So this project was our first time trying to look for Miras for a PL relation with HST, so it was very exploratory. So one of the first things that we discovered, which AGB people probably already knew, was that the HST filter system was very wide, which is good for getting a lot of signal to noise, but it's very bad for actually separating the spectral types of the stars. So if you looked at the LMC with ground-based J and H, you could kind of do pretty good separating oxygen and carbon-rich Miras, but this is not the case for HST. So our Miras that we thought were probably O-rich fall right on top of just like all the other variable stars. And other Miras we weren't sure about in terms of their color or in terms of their spectral classification. And that's because, as you can see, this like F-160 and F-125 filter, they're just in different places. So they didn't really fit well with the molecular bands that are usually useful for distinguishing these two stars. Oh, and as Martha Boyer mentioned, medium bands with HST are great for separating these types of stars, but unfortunately with medium bands, you just have difficulty getting enough signal to noise at the distances that we're looking at, which are really pushing like how far you can see resolved stellar populations. So one thing that we did discover is that if you look at the LMC, it seems like oxygen-rich variables, so these are spectrally identified Miras, have some sort of relationship between spectral type and their amplitude. Like it's a little fuzzy, and we also know that at shorter periods, most of the Miras are going to be oxygen rich. So we really limited ourselves to this little square of stars that we thought were more likely to be oxygen rich than carbon rich. And then secondly, because this was our first try looking at Mira variables with Hubble, we weren't even sure at times if we were detecting real variables or if we were just seeing something become brighter and dimmer over one light cycle. So what we actually did is we also looked at this optical data from 10 years earlier, and we tried to extract the light curves to at least see that it was varying, which we did, and that was comforting. So the end result is another thing we did is compared the distribution of Cepheids and Miras. So this is the ACES field of this galaxy, and you can see the Cepheid distribution really traces like dustier regions or star-forming regions. And the Mira distribution is clearly older, and these white footprints on here are actually the WFC3 IR observations because that's a little bit smaller. And over the course of a year, went through like a full rotation angle. The other thing is we calculated like a 2-point correlation function for the Cepheids and the Miras and found essentially no like detectable grouping here. Okay, so for this galaxy, we created 3 samples, one where we were really sure that they were real variables and Miras and whatnot, because we used optical data and near-infrared data and pretty much everything that we could. And then 2 more where we simulated like basically what if we only had some of the data that we had, because it's expensive to get optical data and near-infrared data. So for future experiments, we might not want to use both. And we found out that this didn't really affect what we got as a 0 point, which was kind of nice and comforting. And And this also suggested that we didn't need the optical data, which we were also hoping to use to remove things that were too red and could be carbon rich. So the next galaxy we looked at was 1559, which I forgot to label on here, but it was the host of Type 1a supernova 2005 DF. And this was at a distance of 19 megaparsecs. So to date, there's still the most distant Mira variables that we found. We had about a year of observations here as well. And in this case, we got only one band because we'd already decided from our previous results that it didn't really seem to matter. Okay. And we found about 115 Miras here. We also avoided this very bright, high surface brightness region because we didn't want to have we didn't want to have confusion from background sources affecting our photometry. Even though we do correct for that, there's a limit to how much we believe our corrections. So this is what the PL relations looked like for 1559. We also refit the 4058 ones because in between this and the previous work, they had updated the maser distance. And then finally, the last galaxy I'll talk about is M101, which is also the most recent one we've looked at. It's a giant spiral galaxy that's been host to the nearest Type 1a supernova. This galaxy has been studied a lot. I think Martha Boyer mentioned other programs looking at it too. And for this one, we have a pretty crazy observational baseline of about 8 years because this galaxy had a very recent supernova and it was also the nearest supernova. So a lot of people looked at the supernova, and these are the previous observations. So we just took a few more on top of this. And what this allowed us to do was to take these widely spaced supernovae observations with some more higher frequency observations to really nail down the periods of some of these stars. And I'm going to skip going through this, but you can ask me questions later. These are just the comparisons between the different galaxies. And their end distribution looked, again, like an older population. So here's what some individual light curves looked like from HST. You can see that like they're pretty sinusoidal, but not perfect. But when you stack them, so this plot might be a little bit confusing to look at, but what I did here is I phased them, like I converted them to phase, and then I stacked all the Miras we found on top of each other, and you see this very nice sinusoidal curve at all periods, which is pretty nice. And by adding in the second Type 1a supernova host galaxy, we also reduced the uncertainty on our Hubble constant, because as you can see here, most of the uncertainty on the Hubble constant measurement actually comes from the Type 1a supernova calibrators, because each Type 1a supernova has an intrinsic uncertainty of about 0.1 magnitudes. And here's what the PL relation looked like for this galaxy. Okay, so one of the best things about this, as I mentioned before, is how often other people have looked at this galaxy. So we were able to compare with previous Cepheid and TRGB measurements and see that the Mira measurements are in quite good agreement with those, which was comforting. And this also kind of indicates, even if the Hubble constant measurements from different methods don't agree, the distances, which are sort of an intermediate step, do. So that actually helps us nail down where the differences are coming from in different distance ladders. And then if we update that plot shown at the beginning with our newest Hubble constant measurement, this is what we get. Okay, now I'll spend like 2 minutes talking about James Webb. So I don't have a paper out about this yet, so this is all preliminary, but we found about basically most of the Miras that we discovered in Hubble in our James Webb field that we got very recently. And here is just like a random slice of the images. So you can see the difference between the quality for HST and JWST. And this isn't a typo, I only had 2 colors, so I just used 2 colors to make a fake RGB image for HST. And here you can see we got observations of M101. The JWST observations are these blue footprints. The original HST observations for Miras are in red. And this program, I also wanted to look at Cepheids. So the Cepheids observed in this galaxy were in green, but I'm not going to talk about them at all today. But we have 6 different JWST bands with NIRCam. And we're hoping that these will be useful for checking whether or not we've really separated the spectral types well. So Martha Boyer's talk was really interesting. For our proposal, we'd used, which I worked on with Massimo Marengo, we used some pet-over models to simulate like which combination of filters would be best at separating oxygen and carbon rich while trying to use filters that were as consistent with Hubble and as wide as possible to have the most consistency with their previous results and to go out as far as possible. And we decided on F150, F115, and F182M. It seems to be working okay. We're not really sure. I still have some more investigation to do on this front to see if this really is separating the way that we thought it should, even though it kind of looks right. And I also just made this plot because I'd seen this in one of Martha Boyer's papers and thought it kind of matched up well with our presumably O-rich and C-rich Miras that we found. Okay, and so my takeaways are, I'll just leave them up here because I think I'm over time, but thank you.
Yeah, it's not a question really, just a point from one of your early slides. So I think, well, I'm sure that the distance measurements with radar have gone at least as far as Mercury.
Oh, okay.
And they used to be used to define the AU before that was fixed at a certain distance. And
Okay.
and I think they also showed that that it rotates sort of with an independent day and isn't tidally locked to the sun. But
Okay,
there we are.
that's good to know. Yeah. I guess they don't use it at all.
Nothing much to do with the rest of your talk.
Yeah. Okay. Cool.
Just a very general question. So it is to do with the Hubble tension, right? So you're just trying to basically narrow anything you can as well as you can. So just reduce error bars wherever you can.
Correct. Yeah.
And so that's the main drive at the moment for the field.
For the field of the Mira distance ladder?
Well,
or just like the Hubble tension field?
I guess
Sorry,
I see it as a one big field. Like,
okay.
is the big driver the fact that the Hubble constant's gone funny again? And so everybody now is looking to reduce error bars and see if there's a systematics. And is this driving the anybody who's trying to do a rung of the ladder better?
Yeah, okay. So I see this as like, why are we trying to improve our measurements of the distance? Yeah, I think it's because two things, one of which I said really briefly is first, in order to like even have a suggestion that there could be new physics, the measurements have to be very good. Because the discrepancy is at 10%, but we don't really consider something new until it's like 5 sigma or whatever. So that implies your measurements have to be like 1% or so to start actually getting new physics. But then the other issue is I think you can make any one measurement really, really good, but I feel like that doesn't eliminate what we're improving is precision and not necessarily accuracy, because we don't know about systematics. So I feel like if we only focus on making one measurement very good, then we're not able to check it for systematic uncertainties. So I think it's important to have multiple independent ways of measuring the Hubble constant, both like early and late, so that Planck and Rees et al., like the Cepheid distance ladder, can be verified. So that's kind of why I started working on this. Although when I started my PhD with Adam, like I don't think the Hubble constant tension had really like happened yet. We were just trying to like see if other independent methods would just agree with the measurement in general. And now that these measurements have all gotten more precise, we keep seeing the discrepancy remain. So I think now the main interest is like, oh, is this really new physics? And like, when do we decide that that's the case? And on some level, it's sociological, and some of it is like, okay, we want to verify as much as we can. Yeah.
Yeah, so there are some galaxies that are quite like NGC 4258, but further away.
4258, you mean Maser galaxies?
Yeah.
Yes.
Are any of those any use to you, or?
I mean, they're not really useful for Miras because NGC 48258 it's too many slides ago, is like the most precise maser galaxy. All the others are much farther away. But there is, oh, right here, it's on here too. There is a maser measurement of the Hubble constant, which is basically using those galaxies to directly measure the Hubble constant with geometry. And right now, this is about 4% uncertainty, which is similar to the Mira measurement right now. That's about as good as they can do at the moment because they're just out of galaxies that they can get really precise maser measurements with. They need something where, like, I think they are able to actually model the disk quite well, and that can be tricky. I think they want something that's mostly edge on, and 4258 like meets a lot of those criteria, and many others don't. So I don't think it'll be useful for Mira's, but they can be their own like non-distance ladder measurement because they're really just one rung.
Thank you for nice talk. I have two quite simple questions. The
Sure.
first is if there's more oxygen-rich Miras or carbon-rich Miras. And the second question is why the amplitude is larger for the carbon Mira than the oxygen Mira?
So those are good questions. Well, first, I think about the ratio of oxygen to carbon rich. I think that was like more relevant to like the metallicity, as people have shown in that plot, where if you have higher metallicity, you're not forming many carbon stars. In our case, since we are looking at galaxies where there's been recent star formation, I think they do tend to be higher metallicity already. They tend to have more oxygen-rich stars, or at least we think so. And that seems to be the case in what we're finding. But really, if you were to look like in the SMC versus the LMC even, the ratios of carbon and oxygen-rich stars in those galaxies are going to be very different. And then secondly, about the amplitude. Yeah, so we thought this was probably because carbon-rich stars are dustier than short period low mass oxygen-rich stars. And that's maybe why the amplitude is smaller for that subset of oxygen-rich stars. I was a little disturbed by that because I couldn't find a ton of information about it in the literature besides just noticing that in the LMC observations. But recently I was talking to Michel Trebucci, and I think he said he might be seeing that in his models as well. So maybe it kind of just makes sense. I don't have a better answer, but I think it does have to do with the amount of dust around the stars.
Thank you.
Yeah.
Which is the biggest factor that influences your error bar? Is according to the period luminosity relation, or is coming from another part?
Yeah, I should have said this more, but I was like, I put in too many slides. So the largest source of uncertainty right now is actually the number of galaxies that we've looked at to get type 1a supernova magnitude or luminosities, because type 1a supernovae themselves have like an intrinsic variation, even after all the standardization, of about 0.1 magnitudes. And even if you include spectroscopy, you can't really do better than that. And so with only one type 1a supernova host galaxy in our first H0 paper, that was by far like the largest source of uncertainty. That's like a 5% uncertainty on its own, and our measurement was like 5.5%. So then, because we're adding all these in quadrature, and so that one just dominates. And even in this case, we have only two now. Yeah, sorry, I got confused seeing this. We have two now, and that's still the largest source of uncertainty you can see among these. So the best thing for us to do is to just get more type 1a supernova host galaxies with Miras. We need some more observations. There's a few other galaxies where that's doable, and Adam has data that he hasn't used, but we haven't gotten around to analyzing that, and I don't think he has any grad students working on it right now. So yeah, I think that would be the best. It goes down as 1 over square root of n right now, essentially, because it's so dominant. Yeah.
Okay, thank you.
Thanks.